Hello everyone. Today we are going to begin with a new module that is nothing but module 4. The chapter's name is Finite Word Length Effects and Digital Filters. As you may be able to see over here that it is a new chapter altogether. So yes, the topic is a little bit small as compared to the previous three modules. So yes, we might get it done a little bit faster over here. And so let's see what is the topic and it's what is it describes. Now first of all, there is a term called as quantization, and there is a question that explain the necessity of quantization process. So before we begin with the quantization process, we need to understand what do we mean by quantization, and what are the various methodologies or errors that we can come across while we are performing quantization, what are the types of different systems that we are going to encounter, so on and so forth. Now if you can properly see that there is a sine graph over here which is being what do you say divided into many which is being what do you say scaled up against certain what do you say step size instructions over here, and what do you say there is a what do you the continuous analog signal over here is being converted into somewhat digital format. Now if you look properly or carefully over here, the actual sine wave value depends what do you say depends on its instantaneous values on the entire sine wave ka graph. But when you compare what do you say when you converted into what is a quantized level signal, then some error is being introduced and it is being rounded off to a nearby value. That is what in simple terms a quantization means. Now let us begin with the actual definition of quantization. Before we begin, I would like my students to what do you say look at this graph carefully, wherein this what do you say the sine graph is known as the input signal or the x of t, wherein and the one over here is written as quantized signal, that is nothing but xq of t. The one q stands over here for quantization. Now it is being divided into certain steps over here. Step size is being given by s over here, and the lowermost point of the signal is represented by VL, wherein the highermost what do you say point of the signal is represented by the term VH over here. Now the process of converting discrete what do you say I'll just give you the definition over here. The process of converting a discrete time continuous amplitude signal into a digital signal by expressing each sample value as a finite number of digits is called quantization. As you can see over here that this what do you say this sample over here is quantized to some what do you say uh, finite number of digits. So this one would be one digit, this one would be the another digit, this one would be the third digit, so on and so forth. Now the error introduced in representing the continuous valued signal by a finite set of discrete value levels is called quantization error or quantization noise. Now but of course if you're plotting a signal over here, then there will be some error because you are approximating it to the nearby digital value, and hence there is an inclusion of some noise over here. What is that noise? We'll also discover that over a period of time. Now quantization over here is a process of approximation or rounding of the sampled signal. Quantization is a process of approximation or rounding off. That means the signal is being rounded off to the nearby value. The sampled signal is applied to a quantizer block. जैसे आपके पास ADC होता है, you have DAC, you have pulse control, you have pulse modulator. Similarly, you have what do you say a quantizer block which quantizes the sampled signal over a period of time. Now what does the quantizer do? The quantizer converts the sampled signal into an approximate quantized signal which consists of only a finite number of pre-decided voltage levels over here. So yes, your quantizer, it simply converts your sampled signal into an approximate signal which consists only a finite number of pre-decided voltage levels. So if you see, this is one voltage level, this is one voltage level, this is another voltage level, this is again another voltage level. These are the various kinds of voltage levels that are being predetermined by the system, and your signal is being approximated to that nearby value. Now each sample value at the input of the quantizer is approximated or rounded off to the nearest standard pre-decided voltage level. These standard levels are known as quantization levels. We'll refer to the figure to understand the process of quantization. But before that, let us consider a couple of more points. The input signal x of t is assumed to have a peak to peak voltage swing of VL to VH volts. Now, this entire voltage range has been divided into Q equal intervals, each of size S. Now, S is called as the step size and its value is given as S is equals to VH minus VL upon Q. Now, in your figure, the quantized value, if you can see over here, this signal over here, just a moment. This signal over here is being quantized from here to here in 8 steps. 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6, 7 and 8 values over here. So yes, it is being divided into 8 sections. So the value of Q over here is mentioned to be 8 over here. Now at the center of these steps, the quantization levels Q0, Q1, Q up till Q7 are located. So if you look carefully over here, the certain levels of at the middle of every quantization level, the quantization levels Q0, Q0, Q1, Q2 up till Q7 are being located. Now over here the signal xq of t. Now this xq of t over here, it represents the quantized version of x of t over here. Now we obtain xq of t at the output of the quantizer. Now when x x of t is in the range of delta 0 over here, then then corresponding to each value of x of t, that is nothing but this analog signal, the quantizer output will be equals to q0. So by that, so every time the signal reaches a lower level, the output would be q0. The signal reaches this level, the output would be q1. The signal reaches this level, similarly q2, and so on and so forth up till the highest point. If your signal reaches the highest point, then you would receive q7 as the output. Now similarly for all the values of x of t in the range of delta 1, similarly for the quantizer output is constant. So for the value of delta 1, or I would say for all the values of x of t in the range of delta 1, the output is constant and is equals to q1. Thus in each range from delta 0 to delta 7, the signal x of t, that is nothing but a sine graph, is rounded off to the nearest quantization levels and the quantized signal is produced. Now the quantized signal xq of t is an approximation of x of t. The difference between them is called the quantization error over here. Now this error should be as small as possible. To minimize the quantization error, we need to reduce the step size, that is nothing but this step size, by increasing the number of quantization levels q. So you can reduce the number of step size over here so that your q can be increased over a period of time. Now why is quantization required? First of all, many times the students ask, sir, जब signal हमारे पास properly है, then in the very first place, why do we require quantization? Now, if we do not use the quantizer block, then we will have to convert each and every sampled value into a unique digital word. Now this will need a large number of bits per word. So for example, if you wanted to convert each and every sample, so if example, if this is one sample over here and now this is one sample over here, so if you don't want to convert it into a quantized level, then for each sample a single word has to be generated of certain bits. Now every bit is consisting of 8 bytes over here. So consider the amount of data to be generated if this simple signal would have to be converted into a single word, and then hundreds and thousands of such words have to be created and then to be processed. So it is a tedious job to be done, hence quantization is being done. Now what are the certain benefits of doing some quantization? Now this will not only increase the bit rate and hence the bandwidth requirement of the channel. Now but of course, now what will increase this if we are not performing quantization, then the bit rate will increase, because the number of generated words would be more, which would be consisting of many bits, and hence the bandwidth requirement of the channel. Now to avoid this, if we use a quantizer with only 256 quantization levels, a predetermined quantization level, so then all the sampled values will be finally approximated into 256 distinct voltage levels. So we don't need to worry about that what will be the a discrete value, or what will be the sampled digital value of your analog signal. So a predetermined say 256 distinct voltage level वाला आपने एक quantizer block select किया, so this will give you a liberty to convert your analog signal into maximum 256 distinct voltage levels over here. Now so we need only 8 bits per word to represent each quantized sample values. Now thus the number of bits per word can be reduced. Now this will eventually reduce the bit rate and the bandwidth requirement. But of course, if my words if my word ka usage is decreasing, then in that case my bit rate and my bandwidth requirement also decreases. Now AD conversion and noise analysis. Now before any DSP algorithm can be performed, first of all, A to D conversion, noise analysis. Now what do we mean by that? While performing a to D conversion, if there is some noise created, we need to perform some analysis on the same. Now before any DSP algorithm can be performed, the signal must be in a digital form. Now most signals are analog in nature, hence analog to digital conversion process is required, which involves the following steps. Now since why do we require analog? Most of the signals are analog in nature. The one which we are listening right now is analog in nature. So yes, the voice, the command, everything is in analog in nature. But in order for processing, in order to upload it, in order to convert it, in order to record it, we need to convert each and every data into some bits, which can be performed by performing the A to D or analog to digital conversion. Now this signal is first sampled, converting the analog signal into a discrete time continuous amplitude signal. The amplitude of each signal sample is quantized into one of the 2 raised to b levels, where b is the number of bits used to represent a sample in the ADC. So now let me read again. Now see what happens is, first of all, your signal is sampled. Now what happens while sampling is you're converting your analog signal into your discrete time continuous amplitude signal. So single discrete signal will be obtained over here. Now the amplitude of each signal sample is quantized, or is being rounded off into one of the 2 raised to b levels, where b would be the number of bits used to represent a sample in your ADC. So your the amplitude could be 4 bits, the amplitude could be of 8 bits, the amplitude could be of 16 bits, depending upon the sample of your ADC. Now the discrete amplitude levels are represented or encoded into direct binary words, each of length b bits. So if you are having 2 raised to 8 levels, so your word over here would be of length 8 bits. So if you are having a level of say 2 raised to 16, so over here each word will be having a length of 16 bits over here. Now so we can say the ADC quantize, then thus the ADC or the analog to digital converter quantizes the analog input signal into a finite number of bits. Now basically from 8, 12 or 16, which gives rise to quantization noise. Now ADC quantization noise also results when the filter input is derived from analog signal. So now it is one of the most common noise, wherein your noise is being the noise is also resulting when the filter input is derived from analog signal. ADC noise limits the signal to noise ratio obtainable. So the converter also limits the noise which is being generated, and the signal to noise ratio, that is nothing but your SNR, signal to noise ratio, which is obtained. Thus the quantization noise power is given by sigma 0 square is equals to sigma square upon 12, which is equals to 2 raised to minus 2b by 13, which is where your q that is being given is the quantization step size, and B is the number of ADC bits that is being used over there. Now, the level of noise can be readily reduced by increasing the number of ADC bits. Now, it is also possible to reduce it using multi-rate techniques. Now, what do we mean by multi-rate? We'll cover in the due course of time. Don't worry. Now, we have a standard equation also. So now, in general, for values of B above 12 bits, the noise due to quantization error is insignificant except for applications such as professional audio where at least 16 bits are required for acceptable performance. Now, the noise due to ADC quantization is fed into a DSP, digital signal processor system, as an irreversible error. The noise power at the output of the DSP system due to the ADC is given by sigma square of sigma ADC ka square, which is equal to sigma 0 ka square 1 upon 2 pi j contour integral of h of z into h of z inverse dz by z, now which is equal to sigma 0 ka square summation k equals to 0 to infinite h square of k. Now, where your sigma square sigma acd ka square is nothing is adc over here. It is a printing mistake, beta. Now, sigma ADC ka square is nothing but your ADC ka quantization noise at the system output, and this one is nothing but a contour integral. H of k is given by impulse response of the system. Now, the term in the square brackets can be termed as a system power gain, which amplifies the ADC noise which is we have derived which we have received by converting your analog signal to digital signal. So the noise is which is being generated while conversion, that noise is known as ADC noise. So depending upon the characteristics of the DSP system over there. Proceeding further, we have a topic called as truncating and rounding. So now, what do we mean by that? Let us see. Now, truncating is a process in which the LSB or the least significant bits are discarded. Consider the 8-bit binary number 1.11000100. Now, it can be truncated into 4-bit binary number as 1.1100. That means the last 4 digits are discarded. Now, rounding operation is performed by selecting a rounding result which is close to the original number. Now, rounding round off once if you are doing rounding off, then but of course जैसे हमें क्वांटाइजेशन नॉइज मिला था या क्वांटाइजेशन एरर मिला था बच्चा, वैसे ही हमें राउंड ऑफ एरर भी मिलेगा. सो वी नीड टू डील विद दैट टू. नाउ व्हाट डू वी मीन बाय राउंड ऑफ एरर्स इन डिजिटल फिल्टर्स? Now, round off errors, first of all let us discuss round off errors. Now, an FIR filter is defined, a sample, we have taken a sample IIR filter, impulse infinite impulse response filter, which is defined by second order difference equation as, which is defined as y of n, which is equals to summation k equals to 0 to 2 b of k x of n minus k minus of summation k equals to 1 to 2 a of k y of n minus k. Now, where your x of n minus k and y minus k are the input and the output data samples, and b of k and a of k are the filter coefficients. Now, in practice, these variables are often represented as fixed point numbers. So typically each of the typically each of these products, b of k and b of k x of n minus k or a of k y of n minus k would require more bits to represent than any of the operands over here. So for example, the product of a capital B bit data and a B bit coefficient is 2b bits long. For recursive system, recursive as in what do we mean by recursive system? Recursive system are those whose output depends on the present and the past inputs present and the past outputs over there. Now, so that is mean by recursive system. So for a recursive system, if this result is not reduced, if not reduced, subsequent computation will cause the number of bits to grow without limit. Now, truncation or rounding is used to quantize the products back to the permissible word length so that the maximum error can be reduced and the noise which has been generated due to the round off or truncation can be limited up to a certain number or up to a certain length. Now, quantizing the product leads to error as we had discussed previously, popularly known as round off errors. Now, in the output data and hence a reduction in the SNR. Now, these errors can also lead to small scale oscillations in the output of digital filter. Now, even when there is no input to filter, these errors can also lead to small scale oscillation. Now, the noise power due to each product quantization is given by sigma r ka square, which is equals to q square by 12 over here. Now, where your r over here, chotu r, this chotu r symbolizes the round off error, and q that is present over here, q square ka q, is the quantization step defined by the word length to which the product is क्वांटाइज. मतलब आपको कौन से पॉइंट तक आपने या कौन से लेवल तक आपने उसे क्वांटाइज किया है वो ये क्यों डिनोट करता है बेटा. नाउ, now we'll proceed further. The next topic is called as input quantization error. So, the question is being asked in such a way that write a short note on input quantization error. Now, the difference between the instantaneous values of the quantized signal and the input is called as quantization error or quantization noise over here. Now, your sigma is given as xq of t minus your x of t, wherein your xq of t is nothing but your quantized signal or the quantized value, yani nazdiki value of the original signal, and here is your original signal. The difference between them is called as the input quantization error. That is the one represented by ripple over here. Now, the quantization error is shown by shaded portion of the waveform in figure 5.1.1, as you can see over here. The one which is present over here, the shaded one, is the quantized error, and the maximum value of quantization error is plus or minus s by 2, where s is the step size over here. Therefore, to reduce the quantization error, we have to reduce the step size that is present over here by increasing the number of quantizable levels q. So, smaller the number of step size over here, जितना छोटा मेरा स्टेप साइज होगा उतना मेरा क्यू का जो क्वांटाइजेशन लेवल होगा वो बढ़ जाएगा. सो यहाँ पे अगर मैंने 8 स्टेप में अगर क्वांटाइजेशन लेवल्स किया था तो मेरे पास 8 स्टेप थे मेरे पास, तो यहाँ पे 8 मेरे पास क्वांटाइजेशन लेवल्स थे. सिमिलरली अगर सपोज 10 या 12 मेरे पास स्टेप्स होते, नॉर्मल स्टेप्स होते, तो मेरे पास 10 या 12 क्वांटाइजेशन लेवल्स होता, विच वुड हैड बीन ईजियर फॉर मी for rounding off or to take it approximately to the nearest value over here. Now, there is a term called as mean square value. Now, the mean square value of the quantization is given by mean square value of quantization error is given by s square upon 12. Now, we will be using this in the formula if needed, where s is a step size and 12 is a standard constant. Now, the relation between the number of the quantization levels q and the number of bits per word, that is nothing but your n, in the transmitted signal can be found out as follows. Now, there is a certain formula over here, because each quantized level is to be converted into a unique n bit digital word, but of course it has to be unique, it cannot be the one which we have received value previously. अगर दो डिजिटल वर्ड का अगर n बिट अगर या एड्रेस सेम हुआ या फिर दो डिजिटल वर्ड का क्वांटाइजेशन का लेवल और स्टेप साइज सेम हुआ, so it would create a problem for us. So now, so each quantization level which is to be converted into a unique n bit digital word, assuming a binary coded output signal. So we are expecting that the output will be nothing but a binary code in the format of 0 and 1 over here. Now the number of quantization levels q is then given by number of combined combinations of bits per word, that is given by a standard formula q, which is equals to 2 raised to the power n. So for example, if your n is equals to 4 over here, then 4 bits per word, that is 4 bits per word, then the number of quantization levels will be 2 raised to 4, that is nothing but 16 over here. So yes, that is for input quantization error. The next topic that we are going to discuss is product quantization error. Now what do we mean by product quantization error? So whenever we are performing multiplication, the multiplication performance, तब हमारे पास एक error generate होता है. Then at that time we say that it is nothing but a product quantization error. Whenever the multiplication operation is done in designing of the digital filter, then the rounding of the result of the multiplication is done. But of course, if you are performing quantization of the entire analog signal, then which is approximated to the nearby value, so the multiplication operation का भी आप nearby value पे round off करोगे. Because of this, the errors are generated. Now these errors are called as product round off errors. So now the quantization of the product of two numbers cause the overflow and the response becomes linear. Now becomes non-linear. Sorry. Now, so in order to obtain the more general result, the quantization errors in the multiplication is modeled as an additive noise sequence, that is nothing but E of n. E of n will represent the quantization error. Now we will consider an additive noise model for the quantization error in a single pole system as shown in the figure. Now your x of n is being given as an input and your output is expected to be a v of n. A feedback is being taken wherein your a v of n minus 1 is nothing but the past input, and E of n is nothing but the quantization error which is being introduced while considering the feedback into consideration. Now we can write the difference equation as follows. Now v of n is equal to a of v n minus 1 plus x of n plus your quantization error being denoted by a of n. Now the effect of rounding the product av of n minus 1 is modeled as a noise sequence E of n, and it is added to the actual output a v of n minus 1. Now equation, that is the one which is present over here, indicate that there are two parts in the output. Now one is the response of the system to the input x of n, and other is the response of the system to the additive quantization noise E of n over here. So if you look carefully over here, one is nothing but the output, one is nothing but the response of x of n, while another one is the response of the quantization noise that is being present over here. Now therefore we can write the equation, the one which we had initially over here, this one we can write this equation v of n, which is equals to a v of n minus 1 plus x of n plus e of n as v of n, which is equals to y of n plus your q of n. Here your y of n is the actual output of the system, which is given by x of n plus your a into v n minus 1, and your q of n will be nothing but the response of the system to the error sequence e of n over here. Now as shown in figure, the error sequence is fed back to the input This reduces the amount of noise power at the output. Now, quantization error. Now, while implementing the filter, what do we mean by coefficient? An important topic. Many a times it has been asked into the exam. So yes, what do we mean by coefficient quantization error? Let's discuss now. While implementing filter in your hardware, the coefficient values must be quantized to the accuracy of digital number system used in your hardware. Now, the filter coefficients should be adjusted depending upon the number of bits supported by the hardware. You cannot have just any random alphabets or any random coefficient, so that and you expect that the hardware should be able to support it. There is a certain system in order. There is a certain set or protocol to be followed. Now, because of this, the error is automatically introduced, which causes the frequency response of the filter to deviate from the desired response. But of course, if you are changing the filter coefficients because the hardware is not supporting it, then there will be a creation of an error. Now, it may happen that the position of poles or zeros may change. Now, how do we minimize such kind of error? Now, the coefficient quantization error can be minimized by realizing higher order filter, or with filters having much higher order of that is nothing but higher values of capital N, with either single pole or double pole filter sections. Now, the single pole filter section have complex poles, as we had seen in the designing of IIR and FIR filter designing chapters. Now, this requires complex arithmetic calculations. Now, to avoid this, complex conjugate poles should be combined to form second order filter sections. Now, what is the effect of quantization on FIR filter coefficients? Now, generally, digital FIR filters are designed such that they have linear phase characteristic in the passband. That means in the passband, the signal would be very much easier to pass, and it is been said that they have a linear phase. That means there won't be any change in your phase when the signal is being passed, when the FIR signal is being FIR when your signal is passed through your FIR filter. Now, if your FIR filters are realized using direct form realization, then the linear phase is maintained even when the quantization of the filter coefficient is done. What do we mean by this direct form? Don't worry, we'll get it done in the numerical section. Now, that means the quantization does not affect the phase characteristics of the FIR filter, but it affects the magnitude response. Now, to avoid this effect, the cascade form realization should be used, and 12 to 14 bits should be used to represent the coefficients. Similarly, the number of bits per coefficient must be increased to maintain the same error in the frequency response characteristic of the filter. So, in order to avoid the quantization error, or I would say the error while converting your quantization coefficients, the cascade form realization should be used, and your 12 to 4 bits should be specifically reserved, or I would say used to represent the coefficients alone. Now, this similarly, the number of bits per coefficient must be increased so that there is a lesser chance of error, and the same kind of error can be expected in the frequency response. So there is no, so once you modulate your hardware, you can easily get your actual input that you are expecting before the quantization error. Now, let us say each filter coefficient is rounded to b plus 1 bits over here. Now, then the maximum error in the coefficient value is bounded as minus of 2 raised to minus of b plus 1, which is less than EH of n, which is less than 2 raised to minus of b plus 1. Now, the error in the frequency response is given as Em of omega, which is equals to summation n equals to 0 to m minus 1 EB of EH of n into e raised to minus j omega n. So this is the frequency response of the quantization error of the coefficients. So yes, now Now, coefficient quantization errors in IIR digital filter. Up till now, this one was the quantization, effect of quantization on FIR filter coefficients. Will proceed for quantization errors in your IIR digital filter. Now, the IIR filter is characterized by the equation as follows: h of z, which is equals to your summation from k equals to 0 to capital N, b of k, z of minus k upon 1 plus summation k equals to 1 to m, a of k, z of minus k. Now, this is a standard equation. Don't worry, we'll cover every topic. Now, when the coefficients are quantized to a finite number of bits, that means the coefficient of the digital signal are being quantized to finite number of bits, the quantized transfer function may be written as h of z for quantized value is given as summation k equals to 0 to n bk of q z raised to minus k upon 1 plus summation k equals to k equals to 1 to m a k of quantized z raised to minus k, where your bk of k is given as bk plus delta bk, and your ak of q is given as ak plus your delta ak. Now, wherein your delta ak and a of delta ak, delta bk and delta ak are the changes in the coefficients b of k and a of k respectively. Now, q denotes over here a quantized coefficient. Now, the primary effect of quantizing filter coefficients using finite number of bits is to alter the position of the poles and zeros of h of z in the z plane. Now, what could happen due to this? The primary effect of quantizing the filter coefficient, that means to round off the filter coefficients to the nearby value using a finite number of bits to alter the position of poles and zeros in the z plane. Now, this could lead to instability, we would say instability or potential instability for higher order filters with sharp transition widths and poles close to the unit circle. Second is a change in the desired frequency response, the one which we would have been expecting. We would not be able to get that, but the one with some minute errors in that. Now, the quantized filter should be analyzed to ensure that its word length is sufficient for both stability and satisfactory frequency response. Now, therefore, the designer should determine the number of bits that are required to repeat the filter coefficients for stability and for the desired frequency response to be satisfied over here. Now, the syllabus topic, the topic that we are going to cover next is zero input and overflow limit cycle oscillation. Zero input and overflow limit cycle oscillation, what do we mean by that? Now, let us discuss. Now, whenever the quantization of filter coefficients is done, the degradation of frequency response takes place. That means the frequency response over a small period of time degrades. It begins to degrade over a period of time. Now, if the if the filter coefficients are not quantized, then the frequency response is not much affected. So, while designing the digital filter, it is required that the filter should have low sensitivity to coefficient quantization. So, if a designer is expecting that the error or that the frequency response should not be much affected, the filter coefficient should not shouldn't be quantized to the highest possible value. It should be to a minimum value. Now, to achieve this, an analog filter is selected in such a manner that it is having inherent low sensitivity. One of the most important and crucial point over here. Yes, please do pay attention, bacha. Now, then such analog filter is converted into the corresponding digital filter over here. Now, it is as good as we were used to design in IIR filter. First, the analog filter was being designed, and then the analog filters were being converted into digital filter. Now, so this digital filter will be less sensitive to the coefficient quantization. Now, Similarly, certain realization methods are used to make the digital filters less sensitive to the coefficient quantization in order so that your frequency response is not affected. Now, consider a digital filter which is characterized by the set of coefficients x of m with the infinite precision by the set of coefficients x of m. Now, with infinite precision realization, let the values of this coefficients be x of r. Now, what do we mean by infinite precision realization? Precision stands for, what do you say, up till how much precise value do we want. So infinite precision realization, that means up till a certain infinite value or up till a certain infinite precise value it is being realized. So now at the condition that your x of m, that is nothing but your set of coefficients, and the infinite precision realization se mile hue coefficient, if they both are equal, the magnitude of the transfer function of the filter is exactly equals to 1. Now, this shows that the transfer function has zero sensitivity. One of the most important point while designing your filters, that it should have low sensitivity to quantization errors. If it has a higher sensitivity, that means the filter is not good enough to quantization errors. Now, limit cycle in IIR filter, it has been asked many times, so yes, please do pay attention beta. Now, the non-linearities, or I would say the error, the noise occur in the output because of the finite precision arithmetic operation. Precision means up to a specific precise value. Now, this causes the periodic oscillations in the output even when the input is 0 or constant. Such oscillation in the recursive system are called as limit cycles. Now, recursive system, as we had discussed previously, that its output depend on present and past output, present and past input over here. Now, this limit cycles occur as a result of quantization effects in the multiplication. Now, when the input sequence x of n becomes 0, then the output of the system enters the limit cycle. So it is as simple as when your input sequence becomes 0, the output of the system enters into a certain cycle called as a limit cycle. Now, the output remains in the limit cycle until another input is applied to the system to drive the system out of the limit cycle. So it's like a continuous circle of the limit cycle. When the system when the input sequence x of n becomes 0, then the output of the system enters into the limit cycle. So in order to break this limit cycle, when another input is applied, the system is the system is made to come out of this limit cycle. Now, there are two types of limit cycle as follows. One of them is granular limit cycle. Let us see. This limit cycle has very low amplitude. The limit cycle occurs when the input is applied to the system is very low. Hence, the word granular came into picture. Now, then we have the the overflow limit cycle. As the name indicates, this limit cycle occurs because of the overflow taking place in the implementation of the digital filters over here. Now, overflow limit cycle, let us discuss first of that. Now, what do we mean? It has been asked many a times, but this limit cycle, overflow limit cycle. So yes, please do pay attention over here. Now, if in the realization of your digital filter, one or more quantizers are used, then it results in a non-linear characteristic. Because if many a times, if you round off the value of the input signal to the nearest quantized level, then but of course there will be the characteristic will be non-linear in nature. This characteristic may be significantly different from that of an ideal characteristic. Now, as a result of finite precision arithmetic operations performed in the digital filter, some registers may overflow when the input signal level becomes very large. Again, a problem when if we are using finite precision method or specified arithmetic operations in the digital filter, then but of course there are registers which may overflow, and what do you say, the input signal, when the input is very much larger in voltage or in very large in number. Now the overflow is defined as when two numbers of b bits are added and the sum cannot be represented by b bits because of the overflow, then the very large positive number becomes a very large negative number and vice versa. Now in case of a recursive system, a feedback connection is present. So if there is an overflow, then it is feedback and what do you say, used to compute the next output when where it causes further overflow. Now this creates undesired oscillation at the output. This results in non-linearity. So if you look carefully, it is nothing but appearing like a simple oscillation kind of a diagram, wherein if you have a recursive system, then the feedback is present from the output to the input. So if there is an output, if there is an overflow at the output, then it is feedback and given to the compute, and so it is fed back to the input to compute the next output, where it again causes overflow. This what do you say, it creates an undesired oscillation at the output. Now this results in non-linearity. Now because of this non-linearity effect, it becomes difficult to analyze the digital filters precisely. Now because of this linearity effect, it becomes difficult to analyze the digital filters precisely. To perform analysis of quantization effects, a statistical characterization of quantization effect is adopted. So yes, dynamic range scaling, we have another kind of what do you say, approximation to be done. Now what happens over here is we have discussed the effect of overflow. Now the overflow causes non-linear distortion and in turn it creates the undesired oscillation which we do not want. Now to limit this overflow, it is required to scale the input signal and unit sample response. This scaling is done between the input and any internal summing node in the system. Now let us assume that y of k denotes the response of the system at kth node for at the kth node, that is at a certain node over here. Now just a moment a bit. Now let us assume that your y of k denotes the response of the system at kth node, that is at a certain node, for the input x of n, and let your hk of n be the impulse response of the system over here. Now then according to the definition of what do you say, convolution, yk of n is given as summation k equals to minus infinity to infinity, minus infinite to infinite, hk of m minus of x of n minus m, that is up till a certain previous value, that is a past input over here. Now taking magnitudes of both the sides, we have yk of n ka mod is equals to summation is equals to under mod summation k equals to minus infinite to infinite hk of m into x of n minus m over here. Now the equations, what do you say, the equation which is present over here can be expressed in terms of summation of magnitude as follows, wherein your yk of n is less than equals to summation m equals to minus infinite to infinite hk of m x of n minus m over here. Now here your x of what do you say, n minus m denotes the input signal delayed by some certain m samples. Now if the input is bounded, then x of n minus m is also bounded. Let this value be a of x over here. Therefore your yk of n, which is less than equals to what do you say, a of x summation m is equals to minus infinite to infinite mod of h of k by m. Please do remember that you don't need to remember this value. It is just for clarification purpose that we have taken into consideration this equation. Now if we want your mod of yk of n to be less than 1, then this condition is satisfied only if your ax of what do you say, ax is less than 1 upon summation of m equals to minus infinite to infinite mod of hk of m. Now this is the necessary and the sufficient condition to prevent the overflow in the system. This main condition over here, wherein your ax is less than 1 upon summation of 1 upon summation from m is equals to minus infinite to infinite hk of m, to prevent the overflow in the system. That means to avoid the overflow, proper dynamic scaling should be done at a particular node over here. So let us take one more topic, so that it becomes easier for us to understand, and we will be proceeding up with a numerical. So yes, now finite word length in digital FIR filters. Now what do we mean by that? Now the difference equation of the FIR filter is given by y of n, which is equals to summation of m equals to 0 to n minus 1. Here summation from m equals to 0 to n minus 1 h of m into x of n minus m, that is the input is delayed by some certain m samples over here. Now where each variable is represented by a fixed number of bits over here. Now typically the input and the output sample, that is nothing but x of n minus m and y of n, are represented by 12 bits and the coefficients by 16 bits in 2's complement format over here. Now it is seen from equation that the output of the filter is obtained as the sum of products h of m and x of n minus m. After each multiplication, the product contains more bits than either h of m or x of n minus m. That is what you would look when we perform the summation of this equation over here. Now for example, if a 12-bit input is multiplied by a 16-bit coefficient, the result is 28 bits long and will need to be quantized back to 16 bits before it can be stored in a memory, or to 12 bits before it can be sent as output of the digital to analog converter. Now this quantization which we have done over here, for example this quantization, it leads to errors whose effects are similar to those of the ADC noise, but it could be more severe in nature. So in order what should be done in order to avoid this effect is the common way. Now, the common way to quantize the result of an arithmetic operation is either one of the two methods. The first method is to truncate the results, that is to retain the most significant higher order bits and to discard the lower order bits, or to round the result, that is to choose the higher order bits close to the unrounded result. This is achieved by adding half an LSB to the result. So first, mostly we will be going for this type of truncating the result. Now round off errors can be minimized by representing all the products exactly with double length registers and then rounding the results after obtaining the final sum, that is after obtaining y of n. So once we receive y of n, then and only then we will be able to say that the round off errors have been minimized. Now this approach introduces a smaller error, that is than the alternative approach of rounding each product separately before summing. So yes, this method do provide an important part in reducing the round off error. So finite word length is one of the most important topics which has to be performed. So let us pick up one sample numerical for this chapter, so that it becomes easier. And generally this type of numerical, this chapter doesn't have any numerical in the final exam, but yes, this type may or may not come into the exam, so it is better we are well prepared for the topic. Now the second order FIR filter has a transfer function such as h of z is equals to 1 upon 1 minus 0.3 z, and it is 0 point beta यहाँ पे एक point missing है. It is 0.3 z inverse into 1 minus 0.35 z inverse. Find the effect of quantization on pole locations of the given system function in the direct form and in the cascade form. The given system has b equals to 5 bits over here. Now case 1, the direct form, we have been given that h of z is equals to 1 upon 1 minus 0.3 z inverse into 1 minus 0.35 z inverse. So On solving, we get 1 upon 1 minus 0.35 z inverse minus 0.3 z inverse plus 0.105 z raised to minus 2. Therefore, your h of z can be written as 1 upon 1 minus 0.65 z inverse plus 0.105 z inverse. For truncation, we have to convert this part, that is nothing but minus 0.65 into binary number. You can directly use your calci also, and here it is being given in a common format which you might have done in DLDA topic. Your 0.65 into since we need to convert this number into binary, we'll multiply this into 2, and the MSB, that is the right hand side part, will be taken out, and the decimal and the digits after the decimal will be multiplied by 2 up till a certain number of time. So 0.65 into 2 will lead to 1.30, 1 being taken out. 0.30 multiplied by 2, 0.6, so 0 is being taken out. Again, 0.6 is multiplied by 2, 1.2, 1 is being taken out. Similarly, the procedure is being carried out, and we did take it up till up till say 6 digits, for example 6 to 7 digits. So it is 1 2 3 4 5 6 7 digits. So your 0.65 in decimal was converted into 0.101001 in binary. So since you have a minus sign over here, so यहाँ पे आप एक 1 लिख दोगे बेटा. Now after truncation, that is we truncated it, so we kept only up to the 3 digits, so it was nothing but 1.101 in binary. Now converting this number into binary converting this number to decimal, we get 0.101 in binary. We need to convert it into decimal, so we'll multiply each number with 2 ka power. So it is nothing but so यहाँ पे the value that you receive is 0.5 plus 0.125. So your 0.101 in binary is converted as 0.625 in your decimal. So your 0.101 is in binary is given as so यहाँ पे आपका 1 आएगा बेटा, your 1. So your 1.101 in binary is converted as 0.625 in decimal over here. Similarly, we convert your we convert the 0.105 which is in decimal into binary, so we get something in binary. Then again, after truncation, we did truncate it to 3 digits over here. So therefore, after converting this binary again to decimal, we get this in decimal. So using equation 1 and 2 and 3, that is equation 1 over here, equation 2 over here, and equation 3 over here, we get h of z is equals to 1 upon 1 minus 0.625 into z inverse over here. Now in cascode form, what do we have in cascode form is h of z is being given by a certain equation. We need to convert this minus 0.3 which is in decimal into binary, so we get the equation something in like this, and then this minus sign is being introduced over here, so this gives 1.010011, and after being truncated to 3 digits, it is the result is 1.010 in binary. Then again, this after truncation, this binary is being again converted to decimal by using by multiplying that certain digits with 2 raised to power. So your 1.012 which was in binary now turned out to be minus of 0.25 in truncation. So similarly, converting minus of 0.35 into your decimal into binary, we get 0.35 which was in decimal, we got it into binary, we reduced that or we truncated the value to only 3 digits, so your value is 1.010 in binary. Now this value again which we have received over here, this value is being taken over here in binary, which it is again then being converted into decimal, and your again a 1 is being added, so a minus sign is being added over here. So using equations 4, 5 and 6, we get that h of z is equals to 1 upon 1 minus 0.25 z inverse into 1 minus 0.25 z inverse. In short, it is nothing but 1 minus 0.25 z inverse ka square over here. So if you look carefully over here, the equation which we had over here was nothing but this equation. So we need to find out the what do you say, the truncation, or I would say the effect of quantization on this equation, which was being reduced to this equation now. So the new equation now for poles and zeros is 1 upon 1 minus 0.5 z inverse ka square. So yes, this is all for the chapter called Finite Word Length Effects in Digital Filter. In the next chapter, we will start with a new module altogether. Up till then, please do be safe. Thank you, beta.